For reasons I don't truly understand, delta functions are a source of discomfort to some of our colleagues. So I'll try to explain them in a very simple way. I mean, there is the mathematics of them if you are unhappy, but there's simply a rule that says, first I'll do it in one dimension. There's a function called delta function, which has following properties. Its value is 1 if I integrate over state space. In this case, it's just one-dimensional interval. Its value is 1 if 0 is part of my interval. And in general, M can be a d-dimensional, X can be a d-dimensional vector, but easiest to first understand in one dimension. It's 0 if the origin is not in the interval I'm integrating over, and it's something to think about if origin is element of what's called the border. In that case, you might have to really think about a representation of these functions, typically a Gaussian, but it could be some other representation, and worry what happens when you evaluate this thing and take appropriate limits. But in general, this is all we need. You just remember that delta function either has value 1 or 0, depending on the interval that we are working. So this is what Dirac delta function is in any dimension. Then there are variations, all of them totally straightforward. And all you really need is that there is some function h of x such that it has a first derivative on the point where you're interested in evaluating delta function. And in our applications, this is usually an easy thing. Now, there could be mathematical settings in which the functions are Lifshitz something and you have to worry about it, but not here. So the simplest version is, suppose you change your coordinates in such a way that you multiply just in one dimension by some number lambda. If this is done on reals, that's just a real number, but a non-zero number. That's crucial. In that case, you can study derivative now of function of x, but a simple linear function. And what you do is you multiply and divide by lambda, and then change the variable, and then the delta function works. And this is clearly 1 over lambda. However, this is a volume measure, so this is always a positive number, so there's an absolute sign. So that's the simplest variation. Now, if you do this in d dimensions, you can imagine there is a linear transformation of the coordinates. And in that case, the integral dx of d, this coordinate, so this is, in this linear case, obviously, just a Jacobian transformation. Then j, you work a little bit, but basic idea is that you can change coordinates by rotation without changing the volume in such a way that you can bring this into diagonal form. And then this is a product of delta functions for each coordinate, giving you the eigenvalues. Coordinate transformation xi, and then you evaluate it for each one of them, and you get product of these things, which you realize you can write as this is a product of eigenvalues, but that's one of the definitions of a determinant of Jacobian. And all that's required is that the eigenvalues of transformation are not equal to 0. Then this makes sense. And the transformation does not, you're used to matrices which are either Hermitian and symmetric, but no, it just has to be any linear transformation such that the eigenvalues of transformation are not 0. So that's very simple. Then you can make it slightly fancier by saying, I would like to look at a general coordinate change, so say of y, this is some smooth function, at least all we'll require is differentiable where we need it. And in this case, it just came from a math seminar in dynamics which did not use a single figure. And I find it rather hard to understand. Actually, it used a figure of, when it used figure, it was trivial. It was on weak KM theorem, and it illustrated by a pendulum in one dimension, where that doesn't illustrate anything. But so here is a figure in one dimension. Imagine that you have a function h of x, where this is x. And that function does whatever it does, but every so often it crosses 0. And let's concentrate on these crosses. So h evaluated x star is 0. Then when I look at dx of delta of h of x, I only care about little neighborhoods. So this is over m. But this can be written as a sum over I, where I have little intervals, mi. And this is interval m star. And it contains my point. And the main thing about this interval is that if the function is smooth and it has first differential, then infinitesimally close to it, I only care about the first derivative of the function. But that means I'm replacing function by first derivative times x there. So that just becomes, using that rule, that just becomes sum of all zeros of this function on the interval m. This is my finite interval where I'm evaluating everything. This is my m. And this is a neighborhood of each small guy. And I get that this is now a sum over derivatives. First derivative evaluated xi, where I is the ith 0, so this is maybe over all zeros of my function hx, and it has to be absolute value. So once we have a definition of Dirac delta function, then it'll also work for functions of the delta function. And all it means is that whenever this is 0, I have local rescaling of the neighborhood. That's just given by the first derivative. And if I do this now in d dimensions, I will...
The superscript on h?
Derivative. So in one dimension, this was discussed in this math seminar because mathematicians ask precisely that. Why do we have a prime on h in BKM theory? This is by definition d of h, d of x, evaluated at point x. And in d dimensions, which I'll write next, we'll call this a Jacobian. Jacobian ij evaluated at x will be d of h I, ith component because I'm mapping vector into vector, over d of xj evaluated at x equals a fixed point. So then this rule now becomes a sum over determinants of J evaluated at alt 0. And this is all we will actually need to know to use Dirac delta functions in the rest of this course. Nothing fancy will happen. So the only thing that we need is that the function, Dirac delta functions, or Dirac deltas of functions, we are considering a once differentiable in neighborhood that we care about them. They could be piecewise differentiable, they could be anything. They just have to be locally differentiable. If you don't know how to define derivative, if you hit some sharp knife edge or cusp, then we have to think about what to do. But this will not be the situation here.